for for small transactions, transactions that have value, but that have enough value, but these intermediate transactions, transactions that has value but don't have like a huge amount of value, but are everyday transactions that you're doing a lot of transactions, so you need these transactions to be cheap and so on. I think that here is the zkEVM is a perfect place to be. And here we include DeFi transactions. Here we include NFT transactions. We're including these even governance and voting transactions. Things that requires a lot of transactions and a lot of transactions, but at the same time require the security of the layer 2. So I think here is the zkEVM is the right place would be the right place to be. So.
Hello and welcome to another episode of Devs Do Something. Today's guest is a good one. We have Jordi Baylina, who leads the technical team building the Polygon zkEVM. The Polygon zkEVM launches in late March, and this episode will serve as a technical introduction into how this particular zkEVM works. So we go really deep into how Jordi and the team pulled this off. We talk through how the prover and sequencer works, step through a sample transaction step by step, and got into just how his team was able to pull off full opcode parity with Ethereum L1 and some of the trade-offs in supporting full EVM compatibility. So if you're interested in deploying on top of the Polygon zkEVM later this month, or just in understanding how it works from a first principles, bottom-up technical point of view, I think you'll really like this episode. So sit back, relax, and I hope you enjoy. As devs, we all love hackathons. They're a great way to boost your skill set, meet other engineers, and add to your portfolio of work. At Superfluid, we've sponsored many hackathons and decided to start putting on a hackathon of our own, the Superfluid Wave Pool. This hackathon is a little bit different though in that it's continuous. It's always open. You can submit any project built on Superfluid at any point throughout the month and have a chance to earn thousands of dollars in prizes depending on how your project stacks up. In just the last couple of months, we've seen dozens of teams build really amazing projects that run the gamut from Superfluid developer tutorials to full-fledged applications to a proof of concept Superfluid StarkNet implementation that we thought was really, really impressive. So we encourage you to check it out today. You can learn more by going to superfluid.finance/wavepool. That's superfluid.finance/wavepool. Happy hacking. All right, so we're here today on this fun Wednesday with Jordi from the Polygon zkEVM team. Welcome, Jordi.
Thank you. It's a pleasure to be here.
Yes, we're super excited to dive into all things zk and the zkEVM. We're super excited for you guys to launch next month. But before we get into all of that, how did you get involved in crypto and in this industry?
It's a long story. So I read the Bitcoin paper maybe in 2013 or something like that. And it was really interesting. But then I went to some meetups and, people there had a lot of other work to do. And the people there were more interested in tax evasion and other nasty things. And I just, had a lot of work to do, so I just put it in the side. At that point, I was just looking at all, and I was trying to write smart contracts in Bitcoin, which is something very painful. Where you discover that most of the opcodes of the Bitcoin opcodes just were not implemented. It was really pain at that time doing anything in Bitcoin. And it was 2015, so 2 years later, that just because a guy, it's called Substack, very known person in the open source space, in a talk in Barcelona, in a JavaScript talk in Barcelona, he was talking about IPFS, something that was not related, but then it was a very interesting topic, and I was just digging and just checking, and then just googling and reading and studying. I just discovered Ethereum at that point, And well, from there it was like a drug, just reading and learning and so on. And at some point I was involved very much in the DAO, in the first, the known project of the DAO. I learned a lot there. Learned about the community. I learned about I meet a lot of interesting people remotely. And at some point, then I got involved I was one of the white hacks of the DAO. So that was like my master degree on blockchains. It was a long story. Explained it a long time ago. And yeah, from there, I just saw that this was my life, and I'm there since full time since there. I just quit. Actually, they fired me in the last job. So yeah, and then I get this is where I want to be. I was fired mainly because I was not doing anything. I was just reading about blockchains and reading about Ethereum, and my brother was kind of my boss, and he just told me, Jordi, what you want to do here? It's just no, I want to be in blockchain. This is my word is I definitively know that's there. So we just make an agreement. And from there, I'm full time. At the beginning, yeah, just doing random jobs, just trying to survive in the space, just trying to go to the conferences. It was the ICO times, and then we created Titan 3 project, and then we created Hermes, and then we joined with Polygon, and here we are, just building the zkEVMs. That's my life.
I love it. Yeah, you've been obviously deeply embedded in the space. I'm sure being a white hat at the DAO was a fascinating experience. That's definitely an interesting master's degree style experience. A little more hands on than a typical master's degree. But
Exactly.
so you've obviously gone very deep into cryptography and into zk, and you know since your time, I guess initially starting out with Hermes and eventually evolving into what's now Polygon's zkEVM efforts. Most of our listeners, I'm sorry, are familiar with zkEVMs and zero knowledge technologies because we have a pretty technical audience. But in your own words, can you just give us a brief description of the Polygon zkEVM, and then we can dive into it deeper from there?
A Polygon zkEVM is a scaling solution. It's a layer 2. It's a rollup. A layer 2 rollup is a zk rollup. There are two types of rollups. Optimistic rollups and zk rollups. This is a zk rollup. And it's just a solution for scaling Ethereum. It's it's not really a chain. It's a chain because there are blocks, but there is no consensus. So we are using the consensus mechanism of layer 1, in this case Ethereum. And on top of that, we are just, we have a system where we can have much more transactions at the same layer 1 without losing any security of the layer 1.
Mm-hmm. And there are some components here we'll get into, right? Like you have the zk node, you do have a consensus contract, and a couple of other things. But maybe before and I guess if you want to correct me on consensus contract.
Well, here the consensus is we need to distinguish between the consensus contract and the consensus algorithm or protocol. So we are not running any consensus algorithm because we are just using the consensus of Ethereum. So the consensus happens in the layer 1. Okay, but how we are building but there is a contract. There is this, we can call it consensus contract or the rollup contract itself. That's actually the rules. This defines the rules of the network. In our case, it's a zkEVM, so the rules are exactly the same or as close as possible as the same rules as Ethereum. So the idea is you have a chain, it's a different chain, and you can send transactions the same way that you are sending to Ethereum. You can deploy smart contracts, you can call those smart contracts and do everything the same that you can do in Ethereum, but you can do it also in this layer 2. Not only that, but that in our case, the zkEVM, where the interesting part and the differential part is that it works exactly like Ethereum. Actually, you connect to MetaMask to the rollup, and you have a network. So from the user perspective, they should not notice any difference that working with a layer 1 or layer 2. But internally, it's different.
Interesting. Well, you guys were able to pull off like full parity, as far as I'm concerned, of like the opcodes, right? So like the opcodes on Ethereum, you effectively have the same opcodes. Obviously, there's a lot of things. Like, what did you guys have to do to pull that off, right? To have this opcode compatibility between what you're doing and Ethereum itself.
Well, mainly it's an engineering, it's a full engineering project. It's an important engineering project, and the idea is, well, we get the explain. So we get the basic technology, which is the zk technology. There is a good simile that's with electronics and computers. Okay, so the basic zk technology would be equivalent to transistors. Okay, so you can do cool things with transistors, but they are really small pieces. And if you want to build something serious, you need a lot of these transistors to put them together. Okay, so the first thing you get is, well, you start with transistors, but then you start having what we call in electronics. Okay, and all the zk projects that we had, so all the zk applications were like doing electronics, small circuits. Here we created, for example, a long time ago, we created Circom, and then you just create some circuit and you do some cool things with that. But um, the step here is, okay, we want to create a circuit, and this is next step. We have electronics, but we want to create a circuit that's actually a processor. So it actually is something that you can process whatever you want. That you just write a program and you run on top of this processor. So the idea is that with these electronics, we built a processor, or if you want, it's a state machine, okay, but it's a sort of a state machines that actually has its own assembly, its own instructions, and you can build this processor if it's doing something. Okay, and with this processor, we created our assembly. So we created a processor, we created an assembly, and we created on top of that a program. We call it a ROM because it's the ROM that's running on this processor. It's a ROM that's emulating, or it's just interpreting. So it's doing what Ethereum does exactly the same way. So this program just takes transactions as an input and process these transactions. If it's a transaction that creates a smart contract, it just modifies the state to create the smart contract. If it's calling a smart contract, it's calling a smart contract. If it's doing a transfer between accounts, that just does the transfer between accounts. But these rules are exactly the same that Ethereum. So it's like another client. It actually we implemented the rules of Ethereum, like Geth or like any Ethereum client, but with this assembly that's running with this special processor in order to create. So this is working with these transistors, with this zero knowledge, and because everything at the end are transistors, and this can be packed as a single proof. Okay, so the result here is a lot of technology, but at the end is a set of layers that we put, and we could do that really fast because there are these layers. So there is people that it's doing the hardware, it's people that's doing the processor, it's people that's doing the ROM. There's people that's running the tests. Actually, we are running the Ethereum test, for example, for checking this ROM interpretation. So it's a full stack of components with different teams working in each of these layers in these stacks. And with this, we are able to create. To have this, but there is a lot of technology and a lot of things we had to solve in order for this to fit in a proof, and this proof to be fast and so on. But this is the main idea, the main architecture in order to build this proof for proving Ethereum transactions.
That's fascinating. So you guys had to basically build your own virtual stack, starting
Exactly.
all the way at the bottom, moving up. And it's interesting that you mentioned you actually had separate teams that were just working on different layers of the stack then, right? So you guys basically split this effort up into people that are really, really good with low-level zk circuits, and then you built it up from there. Is that right?
Yeah, but it's not even so it's that way, but it's even worse because it's an assembly that's a new assembly. So we created the assembly itself. It's a new processor, new assembly, new way of writing hardware. So it's like you are creating a technology, but at the same time you need to learn to use the technology you are creating, which is from the engineering perspective is fascinating, but it's also very challenging and yeah, it takes its time, and it's like you do the things and then you see that you can do it better, and maybe there is something in the layer, but the way you are using the layer, you see, okay, if in this low layer we had this, or we had this in this way, that would be more optimal, and then we switch in one layer, we put it in the other layer, and this has been a lot of back and forth and a lot of communications between the team in order to optimize all the pieces and getting the results where we are right now.
Mm-hmm. Yeah, so you built this entire stack that enables somebody like me or somebody else that knows Solidity to just come in and plug in exactly what they know and build on top of it, right?
Exactly. That's the thing. Is that for developers, is the idea is that developers that are building on top of the zkEVM, they should not notice the difference between working with Ethereum or the zkEVM. You just have your Solidity, but you can use any of the tooling. You don't need to modify the tools. You don't need any special tools. You just use Hardhat, or you just use Remix, or you just use whatever tooling you are using, and it should work straightforward. You connect to MetaMask, you create your accounts, you can have your ledger, you can have everything, and you don't need anything special. So everything is Ethereum. It's Ethereum compatible. It's the same as Ethereum. You don't have any specials to do as a developer.
Mm-hmm. Yeah, there shouldn't be anything else you'd have to necessarily learn from what it sounds like. But one thing that a lot of our listeners like is they like getting very deep into gas golfing, opcodes. A lot of them are into Huff and Yule and these low-level languages. And some of them like literally memorize all of the costs associated with each opcode, and they just like do this for fun, right? Maybe it's useful, maybe it's for fun. But one thing I read about, you have, I think, either a blog post or a page in your docs that was a deep dive into how you guys had to approach pricing for the opcodes. Did you price opcodes like apples to apples, like one-to-one with the same cost, or are they slightly different in terms of pricing, given the different environment?
The model is, so the idea is that, as I told you, we are trying to be as compatible as possible as Ethereum. Okay, so the idea is that from the user perspective, the gas cost is going to be exactly the same that Ethereum is. So from the user perspective, is if doing an ad costs 3 gas units in the zkEVM, the ad is going to cost you 3 gas units. Okay. And this is going to be exactly the same rules that Ethereum has. And this allows us to give full compatibility with Ethereum. Okay. The issue here, and maybe it's a question, is that, okay, the implicit cost, so the real cost for each opcode is not exactly the same that Ethereum. For example, doing a ketchup inside the zkEVM, well, it may be more expensive. Okay. Or doing some operations are cheaper, but some operations are more so it doesn't fit exactly the same relationship. Okay, but we are adjusting that with the gas price. So the idea is that when you are submitting a transaction, I mean, in average, probably the sequencer is going to give you a price, and this price is going to be fine for you. But if you are trying to do exchange transactions, so if you are trying to do exchange things, then the sequencer may tell you, okay, maybe you need to so you need to pay more gas, or maybe this, or just we don't accept this transaction. Again, should only happen if you are doing really crazy things. If you are using normal, so if you are doing a normal program and normal things, you should not notice the difference. And in average, everything will be balanced.
Interesting. Okay, that's good to know. That's really good to know. That's impressive. You guys were able to pull that off, like the full parity, even at the opcode pricing level.
Even I tell you, so the opcodes, of course, there are some exceptions, and there are some things that are a little bit, but there are some exceptions. For example, data availability. We are doing data availability in layer 1, so the cost of data availability, we cannot reduce the cost of data availability because we are putting data availability in layer 1. We don't have data availability, so the cost is the same. Okay, but if you see, there are not that many difference. Doing an exponentiation, for example, in the EVM is already more expensive, and it's very proportional to the cost of doing in zk. So there is a mismatch, but it's not a huge mismatch. So it matches very much. So at the end, if you are doing normal things, this should not be a big issue. But we're also balanced the circuits so that in average matches.
I see. Well, I mean, for the normal application, right? Because of the amount of scalability you're going to provide, these kinds of small things really shouldn't matter. I will say, though, that just because we talked about it, I'm sure somebody's going to go find the edge now and figure out where it gets weird. But I'm sure it'll be edge cases. But one thing that I've found that's been pretty helpful for myself in understanding how new environments work is just asking like someone like yourself to walk through a standard transaction and to maybe step through what actually happens under the hood when a transaction is processed in that environment. So can we maybe walk through again? I know, like, for the developer, if I'm going to call transfer on an ERC20 token, as a Solidity dev, this should be exactly the same, right? The experience should be the same. But under the hood, there's obviously a lot of interesting things happening. So would you be able to walk us through just like a standard ERC20 transfer on the new zkEVM and how that might work at the lower level?
Yeah, first is you probably will have, let's say, MetaMask or your favorite wallet already installed. The same way, you will connect to the zkEVM exactly the same way that you connect to any chain. And you connect with it's going to be a chain that's the same way that you have a mainnet, Goerli testnet, or you have a Polygon POS, or any other chain. You will have the Polygon zkEVM, okay? And you will do a normal transfer. So you will do a normal transfer with MetaMask. You don't need anything special. You can just use MetaMask. So you, from the user perspective, you just do and just create from your wallet, you do your transfer, okay? And this should work. What will happen here? Okay, so let's go deep in this process. Actually, what you are going to do, you are going to take this transaction and you are going to send this transaction to the sequencer. Okay, sequencer is a central party. At the beginning, we can talk later, but at the beginning, it's going to be a centralized sequencer. I don't like the word centralized here because a sequencer, they cannot do many things. So they can decide to put their transaction or not, but they cannot do much more than that. Well, they can solve maybe the transactions, but it's not, they cannot do much. Okay, they cannot even censor you from sending transactions. We will talk maybe later. Okay, so you send the transaction to the sequencer. Okay, and the sequencer will just process this transaction and will give you a block number. So like if if a transaction happened. Okay, so and this will happen really fast. Okay, and you will have like a finality here. That will be very fast. It's a tricky finality because it's centralized. So it's final if you trust a sequencer. Okay, so it's just it's not decentralized system. But if you trust, so the sequencer is promising you that this transaction is going to be included in the chain, and if you trust the sequencer, then you are done. That's it. Okay, but suppose that you don't trust the sequencer, you don't have to. Okay, you shouldn't actually. Okay. Then the sequencer at some point is going to get this transaction together with other transactions, and it's going to put this transaction in Ethereum. Okay, but it's not going to. So they are just going to put the transaction there. Okay, but it's not going to process anything. Okay, but they are just also all the transactions that are processed, that are sequenced, they are going to be at some point in the chain. Okay, this will happen quite often when we are configuring now, but maybe this could be I don't know, a couple of minutes, few minutes, okay, in there. So at that point, the transaction is final, and you don't need to trust the sequencer. You know that this transaction is going to be processed. Okay, so this transaction still has not approved. Actually, anybody, because the transactions are sequenced, and here the rules of processing the transactions are deterministically defined. So all the transactions that are on chain, anybody can process exactly the same way. So anybody can calculate this state, but this state is not on chain. So anybody can calculate it, but this is an implicit state, but not on chain. So everybody knows that this state is going to happen, but it's not on chain. That means that for sure that you don't need to trust a sequencer. You know that this is final, okay? But the only thing that you cannot do is withdraw funds, okay? Because this state is not on chain yet, okay? And here is the third stage is when the prover comes. So it's going to be a prover, okay? That's going to happen, I don't know, maybe once every half an hour. That's going to take all the batches and all the transactions of all the batches, and it's going to create this. It's going to compute this new state and actually prove with a zero knowledge proof that this state is valid. That's correct, and it's going to be on chain. And it's at this point where you will be able to withdraw the funds because you know for sure that this state is valid. So you have like three finality stages. Okay, one centralized finality stages. Let's talk about 2 seconds or really fast. Just centralized. You can just transaction and you just get confirmation. Okay. This can be very useful for many applications, we expect. Okay. Then there is going to be a final, in the sense that you don't need to trust is decentralized finality. So it's a chain. So it's the second stage, okay, and it's going to be like an absolute final or a final where you can withdraw the funds. Okay, it's going to be this third three stage. The second one we are talking about few minutes, and the third stage we are thinking about maybe half an hour, something like that. One proof every half an hour, or something like that. So this is a little bit the process.
Yeah, thank you for that. That's actually really, really helpful, and it's clear too. Like most people who are listening to this can understand that. Now, I heard you say on a talk, right? We can get into maybe some of the scalability bits and some of the other details here. We can come back to the progressive decentralization with the sequencer and all that stuff. But I heard you mention in a talk or a different podcast that the prover itself is really not the bottleneck here because you're parallelizing the proofs, or at least you can.
Exactly.
But what about with the sequencer or with data availability? What are some of the limits or the limitations with scalability with both the sequencer and data availability? Is there anything there that might place a limit?
Yeah. These probably are going to be the next bottlenecks to software. The first one is going to be data availability. Okay. So in data availability, this is what layer ones are trying to solve somehow. Here it's really important, the EIP 4844. Okay. So here is data. This will reduce the cost of the data availability. Okay. It's interesting because the 4844 is putting this data, but not forever. It's just for a couple of weeks, maybe, but it's available. The important part here is that anybody has access. The problem of rollups is that there is this attack that is the data. If somebody is, proving a new state in the rollup, but you don't know which transactions you process. So so you know that the state is valid, but you don't know which is this state, and you don't know where this state comes from. Okay, so then you cannot. There is maybe only one person that can continue moving the rollup, so they can stop the rollups. So that's why it's important that the data is available, and we need just data that if anybody in the world wants to access this data needs to be available. The easiest part here to make this data available is put this data on chain. Actually, we are using right now, we're putting that in the call data as part of the transaction. This is cheaper than doing a normal transaction, but it's still expensive somehow. So here is this limitation, and that's why rollups, and this is common to any rollup, are not as, this is the bottleneck somehow. And this is why it's so important to push with these data availability protocols, EIP 4844, and later on sharding is what should solve the data availability. Okay, and there is this last in bottleneck or thing is that the processing part. Even if you solve data availability, at the end data availability is going to be a cost. It's not going to be, so the limit is going to be how much data availability can Ethereum has. This with sharding should be a lot. In sharding they are talking about 1 or 2 megabytes per second or something like that. So it's like a lot of data you can put in there. But then there is, you have a bunch of transactions and you need to process those transactions. And this is the limit on the sequencer. And these transactions, the problem is that processing these transactions in parallel, so it's not, well, you can do tricks, but it's not possible because transactions, they depend on each other. Okay, and one transaction depends on what another previous transaction did. So something that's not easily parallelizable, you can do some tricks and you can put some fast hardware and everything, but there is a limitation there. Okay, so the number at the end, the number of transactions here is has a limit. But here is there is a lot of things, a lot of research that can be done there, and I would say that without even changing the model, the Ethereum model, this can go really, really, really far, much farther than where we are right now. Okay. If you want to change the Ethereum model, then there are other models that are work better in parallel here. For example, in Polygon, we have Polygon Maiden that's working in this parallelization, but there are other rollups. I think the Fuel Labs, for example, is working in very interesting approaches of this parallelizing data. So there is other projects. So it's our projects and other ideas in the space that are really interesting for this solving this parallelization, execute parallelization. That Vitalik also has some interesting ideas in this front, and yeah, it's a place of research that's. I mean, it's not the bottleneck right now. I think that in the next years we are going to talk a lot about data availability, but maybe in 2-3 years this may become one of the bottlenecks. But we are talking that maybe we can scale easily a couple of orders of magnitude before reaching this point at least.
Interesting. Yeah, that makes sense, especially on the data availability side. That is.
Yeah, that's going to be the topic. In the next year, I expect that availability is EIP 4844 is going to be the topic, and this is going to be really, really important.
For sure. So you mentioned a couple of minutes ago that right now the sequencer is centralized. You have the prover, right? So you have this extra layer of, you don't necessarily have to just trust the sequencer, right? But you mentioned that over time, at least you alluded to this, that over time it might become less centralized. You also mentioned you don't like the term centralized for the sequencer. Maybe you can also unpack that, and we could talk through that.
Yeah. So first is what a sequencer can do. Okay. So the sequencer at the end is receiving the transactions, sorting them, and putting and creating these batches. Okay. Actually, sequencing is just putting what transactions one after the other. Okay. So the first thing is that what the sequencer can do and what cannot do. Well, the first thing is that the system that we are building is censorship resistant. What means with that censorship resistant? It's not like perfect solution but it's at least the sequencer cannot steal the funds, of course, but cannot even log the funds. So imagine that you have funds inside the rollup, and I'm the sequencer, and I'm a kind of a malicious sequencer, or maybe not that malicious. Maybe imagine that you are using Tornado Cash, okay, inside the EVM, and I'm a sequencer, and maybe I just get some threats from some random governments telling me that you cannot process these transactions. Okay? Something that may happen here. Just putting real examples that may happen. Okay, so what happened with your funds? Okay, because I'm a sequencer and I'm not letting you touch your funds. Okay, so here you have an option, and it's an option that anybody has, is that you can send any L2 transaction so you just pack this L2 transaction in an L1 transaction. Okay, so you put this L2 transaction, you put it in an L1 transaction. Of course, you will have to pay an L1 transaction. But once this transaction is in L1, and L1 is censorship resistant, so it's a normal Ethereum transaction, then the sequencer is forced to include this transaction in the chain. Probably this transaction is going to be an exit transaction. So it's okay, you don't let me much, but let me at least take my funds out. Okay, and so the sequencer here has two options. They either include this transaction or they do nothing. Okay, they just stop. Okay, that's another option that they can do. If the sequencer stop, then there is a timeout, and anybody can become a sequencer. So anybody can just generate transactions, and then of course, and of course, if whoever it is, they will be forced to include your transaction. So you are going to get the funds no matter what. Okay, here is not. So this is a solution that we are launching and what we're implementing. It's not a perfect solution, okay? Because I mean, it's censorship resistant, but until a certain point, because the system is not a universal. So I can kick you out of the system, but so I cannot lock your funds or can get your funds, but I can kick you out out of the system somehow. Okay, so and this is not the kind of systems that we want to build. Okay, so we want to build systems that anybody can use it. It's permissionless, so it's like anybody can use it in a normal way. Okay, so here why it's important to have more decentralized sequencers. Okay, but being a centralized sequencer is not that that doesn't mean that you have a centralized system.
I see. You don't have that much power really you can't do a whole lot. You have severe limits on what you can do.
You can do things, but I mean, the worst thing that I can do is just kick you out. This is the worst thing, which is not good. I mean, but it's much better that if I could just lock your funds, for example.
Yeah. Yeah, that makes sense. That makes sense. I think that provides a lot of clarity there. Um, how about, okay, this is a bit of a different topic, but what about this LX to LY bridge design you guys have built? You guys have basically created uh like a bridge architecture to move between the zkEVM and other chains as well, and also obviously L1. But can you talk me through and talk our listeners through what this design is and why you guys focus on it?
Well, this is a very simple design. Actually, it's interesting because it's an idea that's very similar to one of the ideas from the Vitalik and the Ethereum Foundation. But in the beginning, when they start talking about sharding and I'm talking about in 2016 and those times. Okay, so they at that point that we call it these execution environments, and they were talking about sharding, but sharding was not for data availability as we are talking right now. Sharding was more for uh, computation, like having different processors and like having these execution environments, which is more or less what we are doing now when you have maybe multiple rollups connecting one each other. Okay, and at that point we were talking about this communication between these rollups, communication, and it's even more than that. It's even value transferring between these rollups. And the idea how it works is, let me see if I'm able to explain, but the idea is so you mentioned that you have a bridge in L1. So you send the funds to the bridge. The bridge is locked. It's a bridge smart contract. Okay. And then what's doing this smart contract is just adding a new leaf in the Merkle tree, saying, okay, just putting this like a note, saying, okay, this money goes to this roll up, to this roll up, to this account, and this quantity of this token. Okay, so this is like a kind of a note that's inserting. It's not only adding. So this smart contract only adds nodes to this tree. Okay. So, and when a proof is generated, the idea is that when the rollup moves forward, then the root of this tree is transferred to the rollup. Okay, so the root of this tree is information. That means that there is another smart contract inside the rollup, inside the L2, that's actually taking this root and it's saying, okay, there is a leaf, there is a node that's that somebody sends to this account. So I'm this account, so I just claims the tokens in that site. Of course, I just cancel this node. I just nullify it, just say, okay, this node is not, you cannot use it again. I already it's consumed. Okay, and then this is the way you transfer from L1 to L2. But this happens exactly the same mechanism from L2 to L1. So actually, for doing an exit, what you are doing is, okay, there is another smart contract with a tree inside the L2. You send that send that token to the bridge. Okay, if it's then it's creating also a node in a leaf, and then this root is transferred back. So when there is one root that goes from L1 to L2, another root that goes from L2 to L1. So you have this root in L1, and in L1 you can do exactly the same. You just claim in L1 and just mark this node as not used anymore. And you can use that not only for L2 to L1, L1, L2. You can do also from L2 to L2 or for different L2s. And the interesting thing is that it scales very well because no matter how many transactions you are adding to the tree, at the end, every time that there is a proof, you are just communicating one single hash, which is the root of the new tree, and then you are just working with that. This is how the bridge works. It's a very simple idea. These leaves or these nodes can be tokens, but can also be just normal messages. Imagine that you want to transfer NFT or you want to transfer domain name or whatever value or a loan of whatever or some staking, whatever you want. You can implement that with this messaging system, so you can transfer messages and value between the rollups. It's a really simple mechanism. It's a very it's a very cool idea. It's very simple but it's very, very, very flexible and scales very, very.
Mm-hmm. Yep, it's clever, and I think it'll be really useful for application developers, right? That want to take advantage of interoperability and things like that. So, yeah, I
Absolutely.
think that'd be really cool. Okay, maybe a couple other like more macro questions now, but there are lots of different approaches to using zero knowledge proofs to scale blockchains, right? Again, in our conversation with the Starkware team, they decided to go a different route where they didn't focus on EVM equivalents. They built their own system, right? And there are trade-offs to that. So as someone who's spent a lot of time and a lot of effort on fighting for the EVM equivalents, how do you think about the set of trade-offs between maybe doing something more similar to what Starknet is, in comparison to what you've done? Like, what are some of the trade-offs there?
Well, let's see. So 2 years ago, when we started the zkEVM, so that of course it's okay. We want to build this. Okay, so we want to do the zkEVM. Everybody agree that we need that. Okay, but you need to build it, and okay, well, let's build it. Okay, but let's build it is okay. How you build it? Okay, and then you start thinking, okay, what approach we have? Okay, and what are the how would you do it? It's a very engineering question. That is deciding how you do the things. Okay. And here there were nobody think that doing a zk, an opcode equivalent would be possible. This was like a crazy approach by that time. Okay, including myself. If you ask me 2 years ago about this, it's you are crazy. That's not possible. Okay, it's like the technology that was available there was not possible. Okay, so the main two approach that were there were the approach of, okay, let's create a new system. So let's create a new VM and then a new stack on top of that. This is, for example, the approach of Starknet, or the approach that, for example, Polygon Zero were doing at that point, and some other projects were doing. Okay, which is okay. So this doesn't work. Let's start from scratch. Which is okay. It's a valid one, but that means that it's not Ethereum. It's just another thing. Okay, maybe you can do the same things at Ethereum or similar things to Ethereum, but you need to do it in a different way. Okay, different stack, different language, different compiler, and so on. Okay, there were another approach that was also very, probably interesting. Is okay. Let's try to do it. Okay, let's not do it in EVM compatible, but let's do it in a Solidity compiler or Solidity equivalent. Or okay, let's try to that the users are now Solidity and knows how to write a smart contract. So let's try to build something that's similar or something that's the same. Okay, but then at this point we are just compiled to a different machine, and we are just trying to connect there. Okay. And then there were these crazy approach. That's the approach of us. But so I don't know if at that point they already were there, but it was Scroll people and people from the Ethereum Foundation. Actually, I want to give a lot of credit here to Barry Whitehat, who were like spending a lot of hours with him, just trying to solve. Okay, let's try to investigate this approach. Just trying to do an EVM compatible, and we just gone to all the opcodes and just trying to think, okay, who would you solve this and how would you solve that? And just trying to deep in the things that were complex. Okay, and we were just solving things, solving different pieces. Okay, and at some point we realized, okay, no, it's a little bit crazy, but we can. We can apply this technique here. We can apply this technique there, and okay, let's. This looks like possible. Okay, so we come from was impossible to something that's possible. Okay, was difficult, but was possible. So was a good, an important achievement here, and at this point. And here is all the credit to Barry. That's actually the guy that was just convincing me on that. Then, okay, once I was convinced, and then I had to convince here my partners, and because this is a lot of work, and the team, and to work on that. And it was okay. It was possible, and the beginning was the problem was it's possible, but how optimal is it? Okay, because the EVM is not prepared for zk. It was invented at some point that was nothing there. So all these crazy things, how optimal are going to be? Okay, so we are going to make it work, but maybe the other solutions are going to be more optimal, more. Maybe you want to do maybe a token transfer in our system, and our system, the proof may takes like 2 hours, and in the other system, maybe they take like 5 minutes. Okay, so it's like maybe it's possible, but it's not feasible on that. Okay, So, and here is where the main work. So it's just building the zkEVM, and also this is the work of the last 2 years of all the engineers in the Polygon zkEVM team, was about optimizing and trying to do the things in a different way. It was a challenge. It was an every week challenge, or every week we have different challenge, and just trying to solve and squeezing and challenge of all kinds, mathematical challenge, just programming challenges, hardware challenges. How optimize the cache of the CPUs. How we are writing this process so this piece just to go faster. GPUs. So we were trying to just try to investigate all the possible ways and just trying to find the solutions. And this has been a work of lots of engineers for a year and a half, just optimize. Actually, we are continuing this process. And it's interesting because the learn that we had and all the advances that we did in this 1 year and a half, actually, we can say now that we are we are doing the things that are much more optimal than the projects that were following other architectures. Okay, and we have all the compatibility at the same time. Okay, so this is a lot of learning. How you write the storage, how you do arithmetic operations in the 256 fields, how you do memory alignment things, how you do the catch-ups, how you do. So it's a lot of things and a lot of learnings and a lot of small things, small or important things that are inside the zkEVM. And altogether, for example, was something that when we started we didn't know about, but Polygon at some point they also merged with Polygon Zero. They were working with Starks and with these small prime fields. So we switched. We just took all the knowledge of the Polygon Zero, was the Mir project at that time, and so on. All these Goldilocks fields with all the Poseidons that they created, the way they were building these circuits, we got all the knowledge, and we used that in the project. That was, we got a lot of improvements in that in just for this for using this. So when we put this together, it's okay. We have now a prover system that we can. In a single CPU, in a big processor, but a single CPU, we can create a proof of 10 million gas units in less than 2 minutes. When we started, we were talking about hours in creating this. This would be hours in not in one CPU. We were counting with data centers. Okay, so you can imagine the orders of magnitude that we improved at that point. Okay, and again, we didn't even know how far we could get. We knew that there were a lot of things that could be improved, but we are the first one that we are surprised in how much we were able to optimize, to the point that at this point for me, the other approaches makes no sense. So because if you can have opcode compatible, if you can have exactly that you have in Ethereum, why you want to have a different tooling, a different system? It's like you are creating more noise, you are creating more friction for the users. So this is right now is okay. You have an EVM, so and not even that, we are getting every time more closer, every time more similar. This is we are getting more to a type 1 according to Vitalik. So we are getting in that direction. So every time we're getting more similar to what Ethereum it is. This point, we are in a point that the user should not notice the differences. There are some small differences, but they are really small. Some of them we will solve. For example, there is things that, for example, right now we are not implementing pairings in the zkEVM, but we already start working on that. So in the next version, it's going to be pairings there. Okay, and all these things that still remaining, that there is maybe some small differences with Ethereum and things like that. We are just removing these differences. This is one of the work in progress that we are doing. So we expect to have maybe in a year or something like that, we may have a type 1, so a full compatible Ethereum without any differences. That's that's doable. That's that's achievable. And this is the magic of this project.
So with all the innovation here, to stay compatible with Ethereum, and as you guys get closer and closer to having like full complete parity, there's also the fact that Ethereum also might change and add things into the protocol over time as well. I heard you, I think, either say at some place or write someplace that maybe at some point in the future we'll like kind of do an effective freeze on Ethereum. I don't know if that's part of Vitalik and the core team's plans, but how do you think about remaining, or I guess retaining parity with the EVM as the EVM moves over time? Do you think that would be a challenge, or how do you see that?
Well, let's go step by step. The first question, I think, is a very good question for Vitalik or for people from Ethereum Foundation. As far as I know, they at some point Ethereum should be frozen and should be finalized and finished. If you see the roadmap of Ethereum, but the roadmap in the white paper of Ethereum, it finished with that in the white paper is called Serenity, which is sharding. Okay, so expect that once sharding is finished and over, I mean, then Ethereum will be finished. When this will happen? I mean. Who knows? Okay, but it's a roadmap and it's a clear roadmap. Okay, in the wild, Ethereum is going to be hard forks. It's going to be evolutions, and it's a plan for that. Okay, so as while the Ethereum is changing, is adapting, is improving, is doing these modifications in the protocol, we should try to follow up Ethereum somehow. So it's just from the rollups perspective, I think that we need to keep us closer. So if there is something that changed in the EVM, then probably it should be an upgrade, a planet upgrade in the rollups. The same way that there is upgrades in the layer one, should be ways to do upgrades in layer two, in a controlled way, but it should be there. But once Ethereum is frozen, I think then it's when it's time then maybe for the rollups that reach the maturity that we expect, that they also get frozen and we have a fully decentralized system where nobody even can upgrade and just gets public good that people can use is there, and yeah, it belongs to anybody, and that's it.
Makes sense. I think you're correct on the upgrade process for L2 is going to have to be there, right? So you'll probably just take that as it comes. But last question for you, with the mainnet release of the Polygon zkEVM plan for I think March 27th, this is super exciting for you guys. I think this is good timing for this to come out because hopefully our audience will be some of the first people to deploy contracts there. But like, what do you hope people build? Like, what's possible now on the zkEVM that might not have been possible before? Like, what are the couple of use cases that you and the team are most excited to see deployed there in the first year or so?
I would say we will see how this evolves, and this is we are just launching now. But I think that here, let's say for very small value transactions, I think that sidechains like POS or things like that will continue being the way to go. Okay? But if the transactions have would say a small, so if you have a big value, probably L1 still, if you are moving $1 million, I mean, you probably make sense just to keep it, to be stick in the layer one. But for for small transactions, transactions that have value, but that have enough value, but these intermediate transactions that has value but don't have like a huge amount of value, but are everyday transactions that you're doing a lot of transactions, so you need these transactions to be cheap and so on. I think that here is the zkEVM is a perfect place to be. And here we include DeFi transactions. Here we include NFT transactions. We're including these even governance and voting transactions. Things that requires a lot of transactions and a lot of transactions, but at the same time require the security of the layer twos. I think here is the zkEVM is the right place would be the right place to be. So here. But again, we will need to see, and we need to see how this evolves. And sometimes this is a thing of when you are creating infrastructure, you just create infrastructure, you imagine how the people will use it, and then the people just use it in a different way, or you just see usages that you would not ever think about. But that's a cool thing, just that's a good signal that you are doing things that creates real value. When people is using that even in a different way you were thinking for.
I love it. Yeah, I guess we'll see. I'm excited for DeFi in particular. I was going to mention DeFi as an interesting use case here because it fits the bill of these high value but not super high value transactions, right? Maybe the $1 million swaps will happen on L1 still, but everything kind of in the middle where it's these kind of like gas intensive operations normally that people want to do frequently, right? So I think all that stuff will be interesting to see, and obviously we'll see people try to do crazy things as well, which would be fun. But listen, Jordi, we really, really appreciate you coming on today. Is there anything else you'd like to say to our listeners? Anywhere you want to point them online? Anything like that?
Nothing special. Just the people to use the mainnet, the zkEVM. Give it a try. If you're a developer, just give it a try. Just connect your MetaMask and do some transactions there, and just check how easy it is to use it. That's the thing.
I love it. Well, you guys heard the man. Go deploy some contracts on the zkEVM. So, Jordi, thank you again.
Pleasure. Thank you.